we'll continue with importing large models from PCF files. Along the way, I'll show several tools that are available in BOSfluids to make model verification easier. But first, let's have a look at the PCF files themselves. We will open one in a few moments, but in general, PCF files are a text-based file format that includes information on components and at minimum the location and size of components. Information about connectivity, such as couplings or welds, can be saved in the PCF file as well, in addition to, for example, support functionality at certain locations. The bill of material information can be saved within the PCF file, but this is a feature that's more relevant to programs that produce isometrics. Some common programs that are used within the industry to design piping systems are capable of exporting PCF files, such as AutoCAD Plant 3D, Intergraph Smart 3D, Aviva PDMS or E3D, and Caesar 2. There may be more programs that are also capable of exporting the PCF files. And it's up to the user to define which piping information is saved to the PCF files upon exporting. So let's have a look at one of those files. Here I have a folder with a number of files. In total, these are 86 files. And this is what a PCF file will look like. So in the first few lines there will be some definitions about which units are being used, and then there will be some attributes. Then later on there will be specification for example, the first item in this file is a flange, endpoint, there are coordinates, and a size. So all the coordinates are always built up as an east-west coordinate, north-south coordinate, and an elevation. This is the standard definition of PCF files. And then the fourth will be the size. In this case, 125 millimeters. So notice that for each component, in this case the flange, a beginning and an end point are defined, and the length of the component is calculated from the distance between the beginning and the end point. Here there's also some information about the piping spec. It is defined as DRG spec 7, and we'll come back to that later. Welds can also be defined. Within BOSfluids, the weld information isn't really used. And then for piping, similarly, we have two endpoints with the coordinates and the size and the piping specification. So if we open BOSfluids, we can try importing this file. Create a new file. So I'll call it PCF import. And then we'll go to File and Import. Browse to the file that I just opened. Select Open. We have several options when importing PCF files, and some might seem familiar. For example, merge elements we've discussed before, where straight pipe sections can be merged into a single element to reduce the number of elements within your BOSfluids model. Keep miscellaneous, so within the piping component file there can be miscellaneous components, which might be something like a piece of equipment, and there's an option to either keep them or well, remove them. To import restraints, there's an option, and the node increment. So the model that will be built up from this PCF files will contain different all the different nodes, and now we use a standard 10 increment between the nodes. So the model will be the node numbers will be 10, 20, 30, etc. Then there's some advanced settings which can help with solving some issues, and we'll look into those a little bit later. If we select next, then we have the option to define piping specifications, and I'll come back to this later when we import the whole batch of all the PCF files at once. But first, let's look at the imported model. And we can see that all the component files, or all the components, are already in place. If we go back to our text file, we had our first flange at a certain endpoint with a diameter of 125 millimeters, which happens to be this flange. And we can use the tool here to view global coordinates to verify that the coordinates are indeed as they are specified within the PCF file. So I select this tool, and I can now left click on any node within the model, and it'll show me the X, Y, and Z coordinates. Notice that our Y coordinate is our vertical axis. So we expect our elevation to show up as the Y coordinate. We see that that indeed matches. We see our X coordinate, or rather minus X coordinate, matches with the northwest, or sorry, the north-south direction. And by default, north is oriented in the minus X direction when we're importing models from PCF files. And similarly, Z is the east-west direction, but since we have this rotation, now they show up as negative values rather than the positive values that are within the PCF files. Well, that's all very nice, but let's try to make it a little bit more involved and import the rest of the PCF files as well. So when we go again to import, browse, we can select all the files. Then when we press, we use the action replace model. And then we'll see that all the files are listed in this list below here. If you have additional PCF files that are in different folders, you can always select this plus and add more PCF files to this list. So let's focus a little bit on the advanced settings now. There's an option to fix connections, and this is when, through maybe some mistake within the modeling in the program that exported this PCF files, two components don't exactly line up properly. So you might have, for example here, this pipe might be slightly offset from this next component. in the and might be shifted, for example, slightly in the Z direction. By selecting fixed connections, we'll go through all the components, and if they are not labeled as a dead end, but they are a dead end in the model now, we'll try to see if there is another component nearby that it could properly be connected to. And in that case, it will be shifted slightly to line up with the rest of the piping model. If we select include continuations, well, the option speaks for itself. It includes continuations, so some PCF files might include components that are listed as a continuation. If you check this box, those will also be included. Finally, there's an option for resolution. There are some components might have a slight different in their node location compared with the next component. This might happen, for example, if you have two flanges that are connected to each other, and there's a gasket of a few millimeters in between, and the gasket is not exported in the PCF file. So you might have then two flanges that are separated by, for example, 4 millimeters. If we then set this resolution to a value that's slightly above those 4 millimeters, then all the nodes that are found while importing that are within 4 millimeters of each other will be combined into a single node. If we click next, we see some different piping specifications. Also, if components have a unique identifier, they might show up in this list as well. And for the piping specification, we now get to define what the diameters and thicknesses are that correspond with the one diameter property that was in the PCF file. So for example, here we had 125 for this flange. And that flange was within DRG spec 07. So here for the 125 we have the nominal diameter of 141.3 with the standard schedule thickness. The thicknesses that are in this table by default will always be the standard schedule, but of course here now we can change the schedules to whatever we want it to be. And we also have the option to, for each of these specs that we found, to change the pipe material. So we'll have a look, for example, at DRG spec number 3. You can say this is a GRE material or a fiber reinforced piping, and then we can change these sizes accordingly. Now, one fun property of the GRE piping is that the inner diameter is always exactly the nominal size. So a 25 nominal size will have an inner diameter of 25. Then we have for 100 is 106.4, for example. Now, of course, depending on the pipe class, these thicknesses might change, but then the outer diameter has to change as well to make sure that we have the same internal diameter. So this could be our fiberglass piping part of the system. These pipe materials are available in the material database within BOSfluids, and you can make your own material definitions within those database, and they can be selected here as well. Now for DRG spec 7 we can also of course change all the sizes. Well, if we assume that spec 7 is just a steel spec, now we have all the standard schedules here, but maybe we have a slightly higher pressure class, and for example we have defined schedule 80 for all the sizes up to 100. And the same as when we're entering thicknesses in our regular modeling, we can here just use the schedule size and the size will be changed accordingly. Similarly, if we don't want schedule 80, we can also, for example, put XXS for the extra strong, if that's a size that exists within the standard definitions. If you're using the same type of specifications more often, then we can also save these type of tables to a CSV file, and you can do so by pressing this button. You can save it as spec number 7, and then that spec can be loaded from a table as well. If we press finish, we'll first be greeted by some warnings, and let's go through those before looking at the model. The first warning is that some component types were found that are of a type that's unknown, and so in this case it's type coupling, and these are interpreted as rigids. So whenever in the piping component file there's a coupling, it has been imported as a rigid. Similarly, some other types like ISO split point pipeline reference could not be understood and are now as rigids within the model. Another important message that we see is that the imported model consists of 67 disconnected parts. If it's not correct, then try specifying a coarser resolution or enable fixed correction options. So that's the one that we've seen before. The current resolution is 1 millimeter. And here's a list of the node connection descriptions. So within the piping component file, some nodes can have a specified label, and here we have a list of which label exists at which node. These labels are not saved within the model itself, so if these are important to you, then suggest exporting this or copying pasting this to a text file to keep it as a reference. Here we'll see the imported model, and well, let's first go over the method of node numbering. So BOSfluids tries to find the largest header and then start numbering from there. So in this case we have a pretty large, in this case it's almost one, it's a 1 meter diameter pipe that has been that's apparently the largest diameter. So we start numbering our nodes from number 10 onward, and it tries to do the main line and then the smaller branches to keep a more or less consistent numbering. Of course, if you have a very complicated model, then the node numbering at some point might seem a little bit irregular. When we finish the importing, BOSfluids will automatically create groups based on the information in the PCF files. So if we switch over to the edit mode, we'll see here under element groups that there are several custom groups defined, and we'll go over the different types that are defined by default. So first off, there's the parts. So as we mentioned before, this model consists of 67 different parts that are disconnected from each other. We can double click on a part or any group and it will highlight the group itself. And maybe it makes sense that you have disconnected parts, but maybe like here there are some small branches that should have been connected to your main piping. And we can solve that by using the different import options that we discussed before, and I'll go through that in a little bit. So below those 67 groups, there's the different couplings. So these are all the components that were listed as a coupling, and BOSfluids didn't know what to do with it, so they're now modeled as rigids. Then there's also the different pipe specs that we saw. For example, pipe spec number 3, which is the piece of the system that we've now defined as a GRE type material for the piping. And spec number 7 is the largest portion of the system. Then there's also some custom groups that start with ISO, and these are the different PCF files that we have imported. So after ISO there's a colon and then the file name of the PCF file. So if we double click on this one, it will highlight the part of the system that we've imported before in isolation. And in this way it's easy to find the different parts within your system. If for example all your PCFs might have been named after the line number that they have within the system. Then there's some instruments that have been imported. In this case, since it's under an angle, probably a pressure safety valve. There's some other components that were listed as miscellaneous. This looks like a drain of some sort. But as I said before, these have been imported as a pipe, a rigid pipe element. So let's have another look at those disconnected parts. When I selected part number 1 and zoomed into this location, I identified a few elements that were not connected to this part. In general, we can always use our distance tool to find out if two parts are connected. And we can do so if we click it. We'll select the first node and then select the second node. Now if I select, for example, this node over here, we're not connected. I will get a result showing a distance between the two nodes that I've selected, specified in X, Y, and Z direction. But if I select in a similar way two nodes that are connected within this system, then a flow path highlighted in red will be shown, and then besides the XYZ distance between these two nodes, also the shortest flow path will be shown, or the shortest path based on the geometric length, and the flow path. And these two might differ a little bit due to some flow path corrections that are applied when we're looking at T's or T's bands, or if the user has specified a different flow path length for an element. We can now try to correct some of these disconnected parts. So if we import the files again, now I've only selected one of the files, and then I can use this list to add all the rest. And now we can increase the resolution. So we saw that the distance between the resolution in the initial import was 1 millimeter. So we will set it, for example, to 5 millimeters. Now all the nodes that are within 5 millimeters of each other will be grouped into a single node. Now we have again our piping specification. I didn't save pipe spec number 3. So we'll set it to the GRE material, and we can load pipe spec number 7. All the thicknesses are updated as we've input them before. We get some more warning messages, and we see now that the model consists of 64 disconnected parts. We can investigate why those parts are still disconnected. So if we zoom in again on the location where we saw the disconnected parts before, we can once again go to the edit mode, double click this group to show where all the disconnected parts are. So all the highlighted in yellow are part of group 1, and all the blue lines are not connected to it. And we can visualize the different nodes by using the wireframe drawing mode. And in here we can see that there are nodes next to this branch, but this is a single element between these nodes, so there is within this main line not a node here for the branch to connect to, which is the reason why they are not connected within our model. So this would have to be solved. Either we can solve it now by going through all the different small branches and making sure that they have a node to connect to, or within the exporting program we'll have to make sure that there is a node here that's being exported to the PCF file. And let's have another look at some of the verification tools. So we've already used the measurement tool to see if two different parts are connected. We've used the global coordinates. There's also under this eye the show field option. We select show field, then we have this little window popping up where we can select the scope to either model, elements or nodes. Under model we have some options, for example elevation, element length and force pairs. If I select elevation, the model will be colored based on the so the position along the vertical axis. In a similar way we can do an element length, where now all the elements are colored based on their length, and we can right click on an element to specify the length of that specific element. If we go to elements, we also have different options to show for the different elements. For example, the nominal pipe size. Here now all the lines are colored based on which pipe nominal pipe size they have. And we also have the pipe schedule. Same can be done for the diameter. So this just shows the outer diameter, or sorry, the inner diameter. Yeah, so we've re-imported the GRE again, and we didn't update the thickness, so now the exact inner diameters aren't visible. We also have a pipe material. It shows that, well, most of the model is steel except for this part of the system, which is shown in green. We selected the pipe specification that it was a GRE material. And this is a very useful tool to verify that the different parts of your model are modeled as you want them to be. We've already had a little look at the different custom groups that have been predefined by BOSfluids upon importing the PCF files, but there's also other options. So there's, by default, there's the type, where we can select a group. For example, we can select all the valves, and if we, for example, would have all the same valves, we could, for all valves in one action, now set the discharge coefficient. But there's also a little eye here, which we can use to do some model verification or changing. For example, we can select the pipe schedule option, and now we'll be able to select all the elements based on their pipe schedule. Where here we selected all the standard schedule piping, here the XS piping, and here the XXS piping. And now these values can also be changed easily. For example, if we've made a mistake and the XXS piping is actually XS, you can change it. And now when we select the XS piping, all these different parts now have schedule XS. And this method of selecting can be used for all the different element properties that are available here. For example, if we have our complete system set up, we could select the valve opening property. Right now all our valves are on their default value of 100% open, but then we could easily verify which valves have been modeled as open and which ones have been modeled as closed. Last but not least, I would like to show some options for selecting nodes. So if we switch from the elements to the node and boundary conditions tab, we can go to edit and select nodes. Now we have different options for which nodes we want to select. There's end nodes, which are all the nodes that are connected with only one element and are not specified as a dead end or another boundary flow boundary condition. Press select. You can now find basically easily all our all the locations within our model where we currently have a dead end but no flow boundary condition has been defined. This can be an easy way to find the locations of your dead ends or unconnected parts. Note, however, that the small node here is not visible because it's inside of the big pipe. Similarly, in the select nodes, we can also select elbows, which are all the nodes where a change of direction takes place, but are not marked as a bend. And this will probably happen mostly here at these angled valves. We can also select all the T-junctions. So these are all the nodes that connect to three different elements and have not been defined as a type T-junction. If we want to, for all these nodes in one action to define it as a T-junction, we can do it like this, and it's already done. And now that we've defined this as a T-junction, the pressure drop over the T will be calculated properly. And that concludes the different verification tools.